For this video, we're going to demonstrate how to graph square roots and cube roots. We're also going to show you how to calculate the domain and range of each. First of all, this is what a square root parent function looks like. And over here we have a cube root parent function. You can tell it's a cube root because you look at the index here, it's a 3. If we don't have anything written in the index position like this one, we assume it to be 2, which means square root. And parent function just means the most basic look of that function type, and all other functions that we're going to do on this are just some sort of modification of the parent function. So once you know what the parent function looks like or should look like, you should be able to sketch all modifications to it. Now we do have a domain, or how to calculate a domain for a square root, and that domain is anywhere where the radicand is greater than 0. Now the radicand is everything that's written underneath the radical itself. So wherever this bar ends, everything underneath that is the radicand. The range, however, we have to calculate it using the starting domain value. That starting domain value may be the lowest or the highest value depending on which direction the graph is actually going. Now as far as a cube root goes, cube root have all real number domains and all real number ranges. In other words, as x goes infinitely to the right, y it goes infinitely up. As x goes infinitely left, y goes infinitely down, or vice versa, depending on what the modification of the equation is. But we'll show that on the graph. Now the official way to figure out how to graph a square root is to create a table of values. So we're going to do the square root of x, and we're going to come up with a table of values here. Let's go with x here, and you know what, I'm going to change that to f of x. F of x is the output, so I got x here, and I've got f of x there. That's really like the y values. But the numbers that I put in here have to be perfect squares so that I can actually graph them here on my graph. One thing about square roots is you're never allowed to have a negative or take the square root of a negative number. So my lowest x value has to be a 0. So if I put a 0 in there, the output would be 0. Square root of 0 is 0. Next perfect square would be a 1. So if I put a 1 in place of this, f of x or y value would be the square root of 1, which is also 1. The next perfect square above that would be a 4. So if I put a 4 in here, the square root of 4 is 2, so f of x or y would equal 2. Let's go another one. Let's do 9. I can put a 9 in there. The square root of 9 would give us an f of x or y value of 3. Now my graph only goes out to 10, so I'm going to actually stop right here at 9. So let's go ahead and graph those points. So we have a 0, 0 here, a 1, 1 there. We're going to go over 1, 2, 3, 4, up 2, go over 9, and then up 1, 2, 3. And you can see that the parent function of a square root essentially looks like this. So you can see on here that as x goes this way, that's the domain, y is going this way, getting bigger. So the domain of this function would be all x's that are greater than or equal to 0, or we can write it in interval notation, and that would be 0 through positive infinity. And we use the bracket here because this is an equal to sign, and we use the parentheses here for not equal to, and we can never equal infinity. Now the range on here would be all y's that start with this point right here, which is 0, 0. All the y values go up, so all the dots along this line, all the y values on those dots are getting bigger and bigger as x goes out to the right. So we would say that the range would be all y's greater than or equal to 0. And we can also write that as 0, comma, through infinity. So all values of y from 0 through infinity, and this is just interval notation. We'll go ahead and do the same thing with cube root. So the cube root would be, let's say, f of x would equal the cube root of x. And when I go to pick values here, I want to pick perfect cubes. So we're going to put a x here, f of x here, which is the output, which is the same thing as saying y. 0 is a perfect cube, so when I put a 0 there, I will get cube root of 0 is 0. I can put a 1 in there. That's a perfect cube. The cube root of 1 is 1. Next perfect cube above 1 would be 8. Now I put an 8 here. The cube root of 8 is 2, so f of x would equal 2. Now I can't go higher than this. My next perfect cube would be 27. My graph only goes up to 10. So what I'm going to do is actually put negatives. Cube roots, or any root that has an index that is odd, you can actually have negative values underneath here, which means I can go back and put a negative 1 in there. And if I take the cube root of negative 1, my f of x ends up being negative 1. I can also put a negative 8 in there, and the cube root of that would end up being a negative 2. So go ahead and graph these points. 0, 0, 1, 1, 8, 2 will be here. And then negative 1, negative 1, negative 8, negative 2. And what happens here is we have what appears to be almost like what we had up here for the square root on the top side, only it gets a little steeper much quicker. And it kind of goes out this way, and then almost does like a little S shape coming back down this way. And since there's no restrictions on what x values I can put in there, because cube roots you can't have negatives, we say that the domain here is going to be all real numbers. Another way to express that using interval notation would be negative infinity through positive infinity. So as x goes this way infinitely, x can also go that way infinitely. That's why we say all real numbers. But you'll notice the graph is going to go up, which is controlled by our y values. So our range values are going to be infinitely up and infinitely down, which means our range values are going to be all real numbers also. So that would be negative infinity through positive infinity. And every variation of these functions, which is where's the other one right here, is just a variation of the parent function. All right, so we're going to come back over here and start with a couple of examples. So here, let's suppose we have the following. F of x is equal to the square root of x plus 2, and that plus 2 is outside of the square root, so it's not part of the input, it's part of the output. So if we remember back to function transformations, we have vertical transformations and we have horizontal transformations, and anything that happens outside is a vertical transformation. So this means the graph, the parent function, which is this one, has been shifted up 2 units. So if we were to sketch that out, the parent function would start here and go kind of like this. This function, though, would move up 2 units. Its dot would start there and then go out like this. So these transformations we're talking about, in this case up 2, is talking about where does this dot move. It moves up 2 units. The rest of the graph pretty much stays the same. So this is the graph of that function. Now the domain here still starts with x is greater than or equal to 0, because we didn't change anything underneath the radicand, but our y values are actually higher. So instead of y values starting down here at 0, our y's actually started up here at positive 2. So the range on this would be all y's greater than or equal to positive 2, or from 2 through positive infinity. And our domain is still is what it was before. Domain would be all x is greater than or equal to 0, or 0 through infinity. Example 2. Let's suppose we have f of x is equal to the square root of x minus 3. And now you'll see that the minus 3 is actually part of the radical, or underneath the radical. So this is inside affecting x directly, which is horizontal effects. So this graph has been shifted horizontally, left or right. Now let me go ahead and put the parent function on there. Parent function is right here. Goes like that. Now this is a horizontal shift of 3, but it's always the opposite direction of what you see here. So this looks like it should be shifting 3 units left, but this dot is actually going to shift 1, 2, 3 units to the right, and then the rest of the graph is pretty much the same. So this is the transformation from the parent function. This is the parent function right here. This is the function square root of x minus 3. That's what it would look like. Now, as far as the domain goes, remember the domain is where the radicand, which is x minus 3, is greater than or equal to 0. So all we got to do for the domain is solve this for x. So we'll go ahead and put x greater than or equal to positive 3. So this is my domain. And I could also write it as 3 through positive infinity, like that. Now my range is wherever my starting value of the range is wherever my starting value of the domain is calculated. So I have a starting value of domain of 3. So if I put my 3 in place of here and I calculate what the range or the starting range value should be, it'll tell me. So if I put a 3 here, I get 3 minus 3, which is 0. And the square root of 0 means f of x or y, which is range, is 0. So the range starts at 0. And we can see that the range or the y values are still going up as y goes, or as x goes out, y goes up. So we still have y greater than or equal to 0, so that didn't change. Example 3. Let's suppose we have f of x is equal to the square root of x plus 2 minus 4. Now we have a horizontal transformation and a vertical transformation. So let me start with the parent function. Parent function should look about like this. Now remember, the dot is the starting point. That's what's actually going to move. This says move the dot 2 units to the left. So 2 units to the left. And this is 4 units down. So we're going to take the starting dot and move it 2 units to the left and 4 units down, which means that dot now moves to right about here. But the rest of the graph pretty much stays the same. So this is the parent function here, and this is the graph of the square root of x plus 2 minus 4. Okay, so the domain again, domain is going to be wherever x plus 2 is greater than 0. So when I solve that for x, I get x is greater than or equal to negative 2. So all values of x greater than negative 2, so I can write that as negative 2 through positive infinity. Our range values, well, to determine where the starting range value, like I have a starting domain value here, I have to take that starting domain, substitute it into the problem, and calculate where my starting range is. So if I take my negative 2, put it in here, I get negative 2 plus 2, which is 0. And the square root of 0 is 0. 0 minus 4 gives you negative 4, so my starting range value is negative 4. But again, my range values are getting larger, so I'm still looking for y is greater than or equal to. And I could also write that as negative 4 through positive infinity in an interval notation. Example 4, sorry. We're going to do f of x is going to equal a negative square root of, let's just go with regular x, let's go with minus 2 on the outside there. So this right here tells me that we are going to go down 2 units. This times negative 1 out in front is a vertical reflection because it's outside of the x, so it's always a vertical effect when it's outside, but this is timesing all my y values by negative 1, which is going to make them flip or change directions. So the parent function would be here, and normally would go this way. But now we're going to take that and move it down 2 units, so down 2. So this thing is moving down 2, which would be here. But instead of going up this way, negative 1 means it's reflected, so it's actually going down this way. So our domain still starts right here at 0 and goes infinitely to the right. So our domain would be all x is greater than or equal to 0, which is what we can calculate from here. And our range, if I put the 0 here, I get the square root of 0 is 0 times negative 1 is 0. 0 minus 2, I have a range value that starts at negative 2. However, notice that the graph here is actually going down, not up. So all my y values along that line are not bigger than -2, they're actually smaller than or equal to -2. So to show that in interval notation, we'd have the -2 on the right-hand side because that's actually the bigger number, and we would bring that down to -infinity. So this would be -infinity through +2. Negative times on the outside causes a vertical reflection, so it moves down, and instead of curving up this way, it curves down. If I were to put that negative on the inside, it causes a horizontal reflection, so instead of curving this way, it would curve that way, horizontally the opposite direction. One more example here on this, example 5. If we had f of x is equal to, let's say, 2 times the square root of x. This is another transformation, but since this number out in front is a multiply and it's outside of x, it's a vertical effect, but it's not a shift up or down. It's actually a stretching of the graph. So to demonstrate that, we would have, let's say, the parent function looks like this. If I have a times 2, that's changing all my y value outputs to be 2 times as large. So I still start here, but all my outputs become 2 times as large, so it makes this graph steeper. So it's a little bit quicker pickup here at the beginning. It doesn't actually shift the graph anywhere. The same thing would have happened if I put the 2 inside here, only it wouldn't be as steep because I'm actually taking the square root of 2 times the x, but it would make it steeper. Example 6. I'm going to do a cube root. So we have f of x is equal to, let's go with the cube root of, let's go with x plus 1, and let's go with plus 2 here. Okay, so when it's inside, it's horizontal, and it's always opposite. So this is actually going to be left 1, and this is going to be up 2. Now let's sketch the parent function. Remember, the parent function looks kind of like this. That's what the parent of a cube root looks like. So this little dot that I put in the middle is describing this movement right here. So that dot is going to move left 1 and up 2. So that dot actually moves right there, but the rest of the curve pretty much stays the same. So if you're going to sketch these out, that's what that would look like. And the same thing as if we had a negative outside, that would cause a flipping of it vertically. If I had a negative inside, it would cause a flipping horizontally. The only difference with the horizontal flip is we use the y-axis as our line of reflection, so this dot would actually move to this side, and then it would show the graph in reverse.